In this section, we're going to look at the second derivative, which is going to expand on the idea of the derivative taking more than one derivative at one time. So in this section, we're going to interpret the second derivative as concavity, as the rate of change of the first derivative, and as acceleration. We're going to see how the second derivative analyzes our function, just as we did with the first. And we're going to learn how to graph the second derivative, which is going to be the same process of graphing the first derivative. So first, let's introduce what the second derivative is. The second derivative is going to be the derivative of the first derivative. So it's taking the derivative twice. And our notation is f double prime. So we read this as f double prime and that can also be said as the derivative of the derivative. So we said that d dx of something means the derivative of with respect to x. So we are taking the derivative of the derivative. And note that the notation compounds. So if we have d dx of dy dx, we can see that there's kind of like 2d, so we're going to say d squared y dx squared. So we can write this as d squared dx squared of y. And I think that's the best way to think about why is the squared in front of the d on the top, and why is it after the x on the bottom? It's because the operator that we have is d dx squared. So say it's like we're taking the derivative twice, which we can write as d squared dx squared. So this notation can be kind of confusing. There's lots of stuff going on. There's lots of different ways that you can think about it, and I think it's okay to latch on to one that makes sense to you. Another kind of notation that we have is this y prime, y double prime, and that's just to say instead of writing f of x, we could just write the function as y, and we'll say y prime is the derivative, y double prime is the second derivative. Also note that the units of the second derivative are the units of y over the units of x squared, whereas the units of the first derivative are just the units of y over the units of x. So now let's think about what the sign of the second derivative means. So first, let's remember what the sign of the first derivative means. We know that if the first derivative is positive, greater than 0, then we know that f is increasing on that interval. And if f prime is less than 0, f is decreasing. So we're going to use that relationship to build a relationship for f double prime and f prime, because f double prime is the derivative of f prime. So here, instead of writing f prime and f, we're going to write f double prime and f prime. So if f double prime is positive on an interval, then the derivative is increasing on that interval. And if f double prime is less than 0, the derivative is decreasing on that interval. So it's the same relationship, we're just talking about a different function. So this leads us to the idea of concavity, right? And this is what the second derivative is going to tell us about the original function. So let's just say what this is, and then we'll talk about what concave up and concave down actually represent. If f double prime is positive, we know that the first derivative is increasing, and that's going to tell us that f is concave up on that interval. Likewise, if f double prime is less than 0, then we know that f prime is decreasing, and then the graph of f is going to be concave down over that interval. So there are four kind of types of graphs that we're going to look at for this. So let's take a look at this one first. This is a section of a graph, and let's think about what's happening with the derivative. So I'm going to draw some tangent lines going from left to right here. And we can see that these tangent lines, as I go from left to right, start really negative, and they get shallower and shallower, so they're getting closer to 0. So this is going from like really negative toward 0. And that means that the slopes, that's what we're talking about here, the slopes of these tangent lines are getting bigger. The slopes are getting bigger. So that means that the derivative is positive. Or sorry, that's not right. That means that the derivative is increasing, which means that the second derivative is positive. So this is an example of a concave up section of a graph. And note that this is concave up where the original function f is decreasing. So the original function, the black line that I drew at the beginning, was going down from left to right, but the slopes were going up as we go from left to right. This is a concave up where f is decreasing. Let's do another one. So this section of a graph, now we have that f is increasing. But let's think about the slopes of the graph. So here we're going to draw some little tangent lines. And we can see that these tangent lines are all positive. So we're going close to 0 to really positive. That means, again, that the slopes are getting bigger. That means that the derivative is increasing, which again means that the second derivative is positive. So this is another example of a concave up function. What we drew here are the two examples of concave up kind of graphs, one where f is decreasing, one where f is increasing. So now let's draw the idea for concave down. So here's something that's concave down. And note that in this case, f is decreasing. But when we look at the slopes are negative, and they're getting more negatives. This is like going from 0 to really negative. That means that these slopes are getting smaller. Which means that the derivative is decreasing, which means that the second derivative is negative, which means that this is a concave down function. And one more, and maybe you should pause the video, and try to draw what the fourth kind of curve is going to be. That's going to be increasing function that's concave down. And there we have it. So this is going to be f is now increasing. And when we look at the slopes go from really positive close to 0. That means that the slopes are getting smaller. That means that the derivative is decreasing, which means that the second derivative is negative, which means that this is concave down. All right, so I think there's a nice way to sort of remember these shapes as well for concave up and concave down. So here's what I use to remember concave up and concave down. We're going to draw a little smiley face, and note that if the function looks like a smile or any part of a smile, then this is going to be a concave up function. And the stupid little pluses for eyes are telling us that the second derivative is positive. Likewise, if we have a frowny face, that means our curve looks like a frown. Then we have concave down. And the negatives for eyes are telling us that the second derivative is negative. This is a silly way to sort of remember what concave up and concave down functions look like. And it really is just if any piece of the function looks like a smile or a frown, that tells us the concavity. All right. So now let's think about the second derivative as acceleration. So let's review what the derivative is. We let f of t be the position of an object at time t. And we know that the derivative of that function is the velocity of the object at time t. And this is because the derivative of a function measures the rate of change of the function. And that's exactly what velocity is. It's the rate of change of position. We measure how far we go in a certain amount of time. That's the rate of change. So now to think about the second derivative, we need to think about what is the rate of change of velocity. We need to understand how is velocity increasing or decreasing? How much is it increasing? How much is it decreasing? And this is the idea of accelerating or decelerating. If you are accelerating, your velocity is increasing. If you're decelerating, your velocity is decreasing. So let's look at an example to kind of understand these topics more. Let's let f of t be the position of a car at time t. And we're going to sketch the three graphs of f of t, f prime of t, and f double prime of t for a car that has this kind of property. It's going to start at a stop sign, and it's going to go one city block and drive to another stop sign. And we're going to sketch what that's going to look like. So we're going to have the graph for f of t, f prime of t, and f double prime of t. So here the x-axis is going to be t, and we're going to have f of t, this is going to be the distance y for all of these. And we're going to graph f of t here, f prime of t, and f double prime of t. So I think this is a good example for you to try on your own. So please pause the video and try to sketch the graph of the position for this car. Think about where it starts, where it stops, and how it gets there. Once you have that, then try to sketch what's happening with the velocity and the acceleration, as that's what we're doing here. We have the first one is going to be the position. We might think about that as distance from the first stop sign. The second one is going to be velocity. And the second one is, or the second derivative is going to be the acceleration. All right, so now that you've tried that on your own, let's sketch what this is going to look like. So note that for position, we are going to start at 0, and we're going to end at some place, right? That's going to be the first stop sign and the second stop sign. And let's sketch something that may not work. So if you draw just a straight line, let's think about how that would work in real life. This would mean that you are traveling the same speed the entire time. And since you have to start from a stop position, that's impossible. It takes some time to get up to the speed limit, and then you have to decelerate. So that's not going to work. And I think if we think about the derivative and acceleration there, it would kind of not work there as we see the next things. So another way to do this, and kind of what the answer is going to be, is something like this. It takes some time to get going up to speed, so our distance doesn't change a whole lot at the beginning. Then we reach the speed limit, and then we kind of have to slow down so our distance doesn't change a lot at the end. Right. Your graph may look slightly different than this, but this is kind of the basic idea of driving from one stop sign to another. So what's happening with the velocity here? We know that the velocity is starting at 0, and it's going to end at 0. And we know that it is going to increase and then decrease. And it's going to look something like this. Let's try that again. It's going to increase, then decrease. And again, there may be some differences in your graph, but something like that. We start at 0, we end at 0 for the velocity. This is what your speedometer is saying. And note that this would be the speed limit if we are following the rules. We go up to the speed limit. Maybe we stay at the speed limit for a little bit of time, and then we go down. Now let's think about acceleration. So this is what is going on with the change in velocity. So our acceleration at the beginning is going to be the most. We're going to accelerate a lot at the beginning. Then we are going to reach the speed limit, and maybe we'll be at 0 for a little while. And then we're going to start decelerating until we get to the end. So we're accelerating, we get to 0, maybe we go at the speed limit for a little bit of time, and then we start decelerating. And let's look at the signs of the derivative and see if this matches up real quick. So for the original function, this function is always increasing. And that means that the first derivative is positive. It's always above the x-axis, or the t-axis in this case. We can see that the derivative, we have that it goes from increasing to decreasing, which means that our second derivative goes from greater than 0 to less than 0. And lastly, with our idea of concavity, we can see that our original function, we have a concave up portion and we have a concave down portion. And that means that our derivative is increasing and then decreasing, and that matches what we had before. Note that this is a special point where the function changes from concave up to concave down. That's called an inflection point, and we'll learn about that more in chapter 3 and 4. Lastly, we have this idea of not just second derivatives, but higher order derivatives as well. We can do a third derivative, a fourth derivative, a fifth derivative, on and on and on. And just know that if we want to find the third derivative, we are just taking the derivative of the second derivative. And we just keep on doing that forever if we're able to. Some notation for that, we have our prime notation. So f triple prime is just 3 parentheses. But note that at some point, or not parentheses, apostrophes, but at some point, it doesn't make sense to keep on putting those down. Do you really want to write the 7th derivative with 7 little tick marks? Or what about the 70th derivative? At some point, it doesn't really become realistic, so instead, we use this parentheses notation. So if you have a parentheses exponent, that means the derivative. So that would be the 7th derivative. And we usually start that at 4, because at 4 it becomes a little bit cumbersome to draw those tick marks. Note that the notation for the Leibniz notation is you're just increasing the powers of the ddx. You have the second, third, fourth, all the way to the nth power, meaning the nth derivative. In the next video, we'll look at some practice problems related to the second derivative with concavity and acceleration.